Hello everyone, welcome to this new video series. In this series, we are focusing on questions which are going to be exam oriented. If you're revising day before the exam or maybe just learning it for the first time, doesn't matter, then these videos are going to save you a lot of time and help you score big. So get your notebook and let's get started. So first we're going to discuss about order and degree of a differential equation. Let's quickly understand. If I have a derivative which is dy dx, then this is my first order derivative. Similarly, we all know that this is our second order derivative and so on. So we have a differential equation involving all these terms. We want to know what is the order and what is the degree of the differential equation. The very first rule is that in the differential equation, the derivatives must have integral power. That means the powers must be integer, they cannot be fractions. That's the very first thing we need to keep in our mind. So here I can see that all the powers of the derivatives are in form of integers. So we have integral powers of the derivatives. So if we look at this particular term, we can see that the order here is 3. And that's the highest order that we have because this term is of order 1. So the highest derivative is third order. So that means the order we have is 3. And what is degree? Degree is the power of the highest order. You can see the term which has the highest order has a power of 1. So that means degree is 1. Okay. Degree is not the highest power available of any order. It must be the power of the highest order. Okay, so the highest order is third order in this differential equation and the power of that particular term is 1. So degree is going to be 1. So if we look at the second example, here we can see that the derivative present is only dy dx. That means only the first order derivative is present and its power is 5. So that would mean this is first order and degree is 5, right? Now if we look at the last example, here we can see we have a non-integral power of a derivative. So first we need to make sure we don't have a non-integral power. So what we can do is we can write it in this way, d2y dx square, and we can take rest all the terms on the right hand side. So that would be e to the power x minus 6 dy dx minus 8y. Now we can raise a power of 2 on both sides to get rid of the 3 by 2. To get rid of this 2 in the power, we want to get rid of the fractional part. So we need to do a whole square on both sides. So if I do a whole square on both sides, so we end up with something like this. So the 2 gets cancelled in the power and we are left with d2y by dx square whole cube equals e to the power x minus 6 dy dx minus 8y and a whole square, right? So now here we can see that the highest order present is this particular term which has a order of 2 and its corresponding power is 3. So that means this particular differential equation has order 2 and degree 3. So the most important thing here is that we had to get rid of the fractional power from the derivative. All the terms in the differential equation, all the derivative terms must have integral power before we decide what is the order and degree. Okay, so let's move on from here. Next, our topic is linear differential equation. What is the meaning of linear differential equation? It is a differential equation where the dependent variable must not be present in a non-linear format. So now what is a dependent and independent variable? When I have a derivative dy dx, then y is my dependent variable and x is my independent variable. Okay, so whenever I have a differential equation, the dependent variable must not be present in a non-linear format. Non-linear in the sense y to the power 2, that's non-linear. Any higher power of the dependent term is non-linear. If I say, so basically I can say y to the power n, where n greater or equals to, that makes it non-linear. y multiplied with a dy dx, that makes it a non-linear. Y to the power any n where n belongs to any natural number multiplied with dy dx, that makes it non-linear. Okay, not only natural number, it can be negative integer also, it can be fractional value also. Okay, so I shouldn't mention n belongs to natural number. N can be basically any power multiplied with dy dx, that makes it non-linear. Okay, so and if I have sine y, tan y, or let's say e to the power y or log y, all these are transcendental terms and these make the differential equation non-linear. So these terms should not be present in the differential equation. Okay, all these terms involving the dependent variable should not be present. The dependent variable can only be present in the derivative and not anything multiplied with it, or it may be simply present as the term y multiplied with whatever function of x. Okay, x is our independent variable, so independent variable may be present in any format, that doesn't create any problem for us, but we have to make sure that the dependent variable in the differential equation has to be present in a linear format, not in a non-linear format or not in form of transcendental terms. Okay, so ideally a linear differential equation is something which looks like this, where we have it may have the nth derivative of y with respect to x, where x is the independent variable, and multiplied with any function of x, not a problem. These functions of x can be non-linear and we don't have any issues with that. Okay, the non-linearity should not be present in the dependent variable term, it can be present in the independent variable term. So this is the basic structure of a linear differential equation. Okay, so moving on from here, so now I have a set of equations and I need to comment whether these are linear or non-linear differential equations. Here I can see the dependent variable is y and it is present in a linear format. There is no non-linearity involving the dependent variable, so this is definitely a linear differential equation. Okay, if we look at the second example over here, then again the dependent variable y is only present in the derivative and there is no non-linearity involving the dependent variable. I can see function of x, which is in the non-linear format, is multiplied with the derivatives, that's not a problem. The dependent variables are in a linear format, so this is again a linear differential equation. If we look at the third example, then this is not a linear differential equation. Why? Because I can see a higher power of derivative has become involved in the question. So that means the dependent variable is y, it is in the derivative and it has a higher power, and higher power makes it non-linear. So this is an example of a non-linear differential equation. Okay, so I hope you understand the difference between a linear and a non-linear differential equation. So let's move on from now. We are going to focus on formation of differential equations. So that means some conditions will be given to us and we have to form a differential equation from there, either by utilizing the given condition or by removing some constants which are present in a given equation. Okay, so in this first question we can see that it's saying eliminate the arbitrary constant a and b. So a and b are arbitrary constants, we need to get rid of them and create a differential equation. Okay, now one thing to remember over here is that if I have 5 unknown constants, then the order of the differential equation will be 5, because in order to remove all the constants I have to do the derivative that many number of times to get rid of all the constants. So that means I will end up with a 5 order differential equation. Okay, so here I can see I have 2 constants. So if I have to remove the 2 constants, I have to do derivative 2 times and I must be ending up with a second order differential equation. So this is something we should know right before we start doing the problem. Okay, now let's get started with it. So the approach to solve these kind of questions is that we directly start differentiating the given equation. Okay, so we have y equals a e to the power 2x plus b to the power minus 2x. We start doing a derivative both sides. So that would be dy dx equals 2a e to the power 2x minus 2b e to the power minus 2x. Okay, so we can take a 2 common and do another derivative. Okay, so let's do another derivative, which would be d2y dx square, a 2 fully taken common, and again we would get 2a to the power 2x minus minus, it would become plus, so plus 2b e to the power minus 2x, and I can see this is same as y, okay, provided I take the 2 common. Okay, so if I take the 2 common, I have got back my first equation. So that means I have got back d2y dx square equals 2 taken common, it will be 4, and we get back y, right? So this is our required differential equation. Okay, so given the equation, we create its corresponding differential equation. Now if the question said that solve this differential equation, then solving this differential equation would mean that you start from here and you reach right over here. So if you just go backwards, you get the solution of the differential equation. So this is basically nothing but the solution was given to us, we created the differential equation. It can be the reverse way also. So to go from here to the solution, you understand that we have to integrate 2 times to reach the solution. Okay, so we will go into that slowly. That's all about differential equation, solving differential equation. But first let's discuss how we can go from solution to the differential equation. Solving the differential equation is a completely different ball game. We will be slowly dealing with that. So let's take a look at another question. It's saying that obtain the differential equation of all circles, each of which touches the axis of x at the origin. Okay, so that means the circles touches the axis of x at the origin, and I need to create a differential equation of all such circles. So that means basically I have a family of circles, right? I have to draw all such circles which touches the origin, which touches the x-axis at the origin. So that means the circle can be something like this, the circle can be bigger, the circle can be much smaller. So I basically have a family of circles, and I need to make a differential equation which represents this family of circles. Okay, basically the solution of that differential equation would represent this family of circles. Okay, so I need to form the equation first. From there I need to reach the differential equation. What we can do is, let's take one specific circle and deal with that. So let's say this is one of the required circles, okay, which satisfies the given criteria. Let's say the radius is r units. Okay, so obviously if the circle is touching the x-axis at the origin, so that means the center would be lying on the y-axis. So the center lies on the y-axis, and let's say its coordinate must be 0 comma, if the radius is r, then 0 comma r, right? So I have a circle whose center is 0 comma r and whose radius is r units. So the equation of a circle like this would be y minus r whole square plus x minus 0 whole square equals to r square, right? Because the center is 0 comma r, so x subtracted from 0 and y subtracted with r whole squares equals to radius square, right? Because the equation of a circle is x minus x1 whole square plus y minus y1 whole square equals to radius square. So I've just used that formula, right? So that would give me x square plus y square minus 2yr plus r square equals r square. I can cancel out the r square from both sides, and I have x square plus y square minus 2yr equals 0. So I can see I have just one constant over here, one unknown constant, which is r, right? So that means I can say from beforehand that my differential equation is going to be a first order differential equation, because I just have to eliminate one constant. Alright, so let's differentiate this both sides with respect to x. So I would get a 2x plus y square. If I differentiate, I would get 2y I'm differentiating with respect to x, so dy dx minus 2 r dy dx equals 0, right? So from here what I can do is I can get rid of the 2 first, and then I can find the value of this r. After I find the value of this r, I can plug it in the first equation again, right? So I will just take the bring that r on that side, so r dy dx, that would be x plus y dy dx. So r, so I will not be writing dy dx from now on. To save some time, I'll be writing dy dx as y1 and similarly d2y dx2 as y2. Okay, so r is x plus y1 upon y1, right? So once I have got this value of r, I can plug it back to the main equation or the first equation that I had. So I can plug the value of r right over here, which is this value. So the equation would become y minus x plus y1 upon y1 and a whole square plus x square equals to x plus y1 upon y1 whole square, right? So if I do a little bit of simplification, so y1 minus x minus y1 upon y1 whole square plus x square equals x plus y1 upon y1 whole square, right? So I can do a little bit more simplification over here. I can do LCM, and that would give me so the y1 would cancel, and I will be having x square by y1 square plus x square equals x plus y1 on y1 whole square. Let's multiply a y1 square all over, so that would be x square plus x square y1 square equals to x plus y1 whole square. And let's not simplify this any further, let's keep it up till here. And so this is our required differential equation, which represents the family of all the circles which touches the y-axis at the origin. Okay, so this is how we form differential equations. All right, so now moving on from here, our next topic is to understand whether a differential equation is exact or non-exact. Okay, so to solve a differential equation of, you need to keep in mind first order and first degree. So we are right now trying to solve differential equation of first order and first degree, nothing more than that. Okay, the more the order and more the degree, the complexity of the solution would increase. So we'll go step by step. First we are trying to solve first order first degree. To solve a differential equation of first order first degree, the very first thing we need to look into is whether it is exact differential equation or a non-exact differential equation. If it is exact, okay, if the differential equation is exact, then the solution would be much easy. Okay, it's a direct process. If the differential equation is non-exact, then it's not so directly easy. It involves an integrating factor, which we write in short IF for integrating factor. After finding the integrating factor and using it in the question, then we can reach our solution. So we don't reach the solution directly. There is an intermediate step of finding integrating factor. Alright, so let's discuss this in details. So first let's talk about exact differential equation. What is the meaning of exact differential equation? So if I have a differential equation of first order first degree, we can always write it in this format: m dx plus n dy equals 0, where m is a function of x and y, n is also a function of x and y. Okay, so basically we just split the dy dx into two parts by, you can understand, if I multiply dx on both sides and we split it, so the differential equation would look something like this, provided if it's first order and first degree. We can always arrange it in this format. Okay, so once it is arranged in this format, now we want to know whether this differential equation can be written in the form d of something, let's say some function of xy equals any constant. Okay, that constant can be 0, non-zero, any constant. The question is, can we write this differential equation in this format? If the answer to this question, is yes, then that differential equation is called an exact differential equation. If the answer to this question is no, then that differential equation is called a non-exact differential equation. So if it is non-exact, now since we cannot express it in this way, so that means we cannot directly solve it, so we will need further manipulation into that using integrating factors. Okay. But if we can write this differential equation in this format, then you can see if we reach this step, we can just do an integration both sides and we would reach our answer. So if it is exact, we can directly reach our answer with after arranging it in this way and integrating both sides. Okay. So now the question is, if I look at a differential equation, how will I understand whether it is exact or non-exact? Okay. So to understand that, this is the required criteria. Okay. So firstly, we need to arrange our differential equation in this format. Once it is arranged in this format, the function which is associated with dx, we need to partially differentiate that with respect to y. Just remember, it's opposite. The term associated with dx has to be partially differentiated with respect to y. The term associated with dy, that has to be partially differentiated with respect to x. So they are just opposite. And if they are same, then the differential equation is exact, otherwise not. Okay, and once it is exact, then the solution process is very easy. I'll tell you that right now with one question that we will be solving. So let's look at this differential equation. First we need to check whether this is exact or not, and then hence we need to solve it. Okay, so first let's examine whether it is exact or not. So the part associated with the dx, that's our m part, and the part associated with dy, that's our n part, right? So the first thing we need to do is we need to find out del m del y and del n del x and check whether they are same or not. So we need to find out del m del y. So that would be del y of y e to the power x, right? Now we are partially differentiating with respect to y. Now what does that mean? That means other than y, if any other variable is present, it has to be treated like a constant, right? So x is treated like a constant, so that means e to the power x is treated like a constant in this derivative, so I can just bring it outside the derivative. So that would be e to the power x partial derivative of y, and derivative of y would be 1, so that means we would be getting e to the power x. Now del n del x, that would be del x of our n is 2y plus e to the power x, right? So now again 2y, now y with respect to x, so that has to be treated like a constant. So derivative of a constant is 0, so derivative of 2y with respect to x will be 0, and derivative of e to the power x with respect to e to the power x, with respect to x is e to the power x, right? So we have got both our del m del y and del n del x equal. So that means this differential equation is definitely an exact differential equation. Okay, so once we have understood that this is exact, now the process for solving is quite easy. What we'll be doing is we need to directly integrate the m function with respect to x. Okay, but remember, here in this integration we will be treating y as constant. Okay, in this integration any y term has to be treated like a constant. So what is our m? M is y e to the power x dx, and I need to treat any y present here like a constant. So that means this y is a constant, it will just go outside the integration. Basically we have integration e to the power x, so that would be y is a constant and integration of e to the power x would be e to the power x. We will not give any integrating constant here for now, we will give it right at the end. Okay, so now in a similar fashion we'll be doing integration in dy, where we'll be treating x as constant. Okay, so our n term is 2y e to the power x, 2y plus e to the power x dy, right? where we are going to treat x like a constant. So that means e to the power x is like a constant. So its integration would be y into the power x. So first let's do the integration of y. Integration of y would be y square upon 2. The 2 will be cancelled. So we'll have y square plus integration of e to the power x. E to the power x is a constant. So it will remain as it is. And integration with respect to y, we'll be getting one y. Okay. Now our final answer. For the answer to this differential equation, we need to look at the two terms that we have got from the two integrations that we have got. So what we'll do, the easiest way is, let's just write whatever we have got from the first integration. That means doing the integration of m dx, we have got y e to the power x plus, now again we will write the terms that we have got in the second integration, provided we will not copy any term which has already been written. That means y to the power x is present in the first term in the first integration. It is again present in the second integration. So we will not be copying it for the second time again. Any same term that we have got, we'll copy it only once. Okay. So you can treat this like union of two sets. Okay. Suppose this is one set, this is another set. So if I tell you to do the union of the two sets, you will not write the same element again and again. Any one element, if it is written once, you will not write it again. Okay, that's the simple thing you can keep in your mind. So y to the power x is already written. Y square is a new term, so we'll write y square. We will not write this term again because it's already written. So once all the terms are written at least once, we will write equals c, where c is our constant. Okay, c is the integrating constant, and that's the solution to the given differential equation. Now remember, our differential equation was first order differential equation, so that means only one constant will be present, not more than that. Okay, so let's do another quick question of this. So this differential equation is given, we need to check its exactness and hence solve. So I would advise everyone to pause your screen here, solve it, and then again resume the video and watch the answer. Okay. So you can see this is our m part and this is our n part. So first I'll be doing del m del y, and that would be del y of e to the power x sine y. E to the power x will be treated like a constant, so we'll only do the derivative of sine y, that will be cos y. So we have e to the power x cos y del n del x, that would be del x of e to the power x plus 1 into cos y. So in this case, cos y will be treated like a constant. We'll be only differentiating e to the power x and 1. Derivative of 1 would be 0. So derivative of e to the power x is e to the power x. Derivative of 1 is 0. And cos y remains like a constant. So that means e to the power x cos y. You can see we have got the same answer. So del m del y equals del n del x. That means the given differential equation is definitely exact. Okay, now we need to solve this. Again, same technique. We need to do first of all integration m dx. In this integration, y should be treated like a constant. So that would be integration e to the power x sine y dx. Y constant, so that means sine y will go outside the integration and we'll be having e to the power x sine y. Then coming to integration n dy, where x should be treated like a constant and we have n as e to the power x plus 1 cos y dy. Right, here x is treated like a constant, so that means we have to break this integration into two parts. We have e to the power x cos y plus cos y dy. Right, so e to the power x is constant, so for the first case e to the power x goes outside and I have integration of cos y, that would be sine y, and again integration of cos y, that will be sine y, plus, and no constant right now, we'll add the constant right at the end. So now if I combine these two things, okay, so we have got this as one part of the answer and this has one part of the answer. So our general solution would be first I'll write the term I've got from the first integration, which is e to the power x sine y. This same term is again present over here, so I'll not copy the same term again. I'll go for the next term, which is just sine y, so plus sine y equals constant c, and this is our final answer. So I hope you understand how we are solving exact differential equations. Next, we will be solving non-exact differential equations. For that, there are several rules for finding the integrating factor. So let's check out the rules of finding integrating factor in the next video. See you again.